had some kind of test today or something?
No, we are just that. I guess at least some of us.
Okay,
Yeah.
I see. Well, that's okay. I mean, that should be something that you should get used to. This simply means that you're students. Okay. Well, I see there are a lot of us currently, so I think we should start. Yeah, so I just want to say a couple of general words at the beginning. So I just want to explain something regarding the Grosvenor basis theory. So first of all, this is, well, why do I discuss Grosvenor basis? Well, because this is a gentle introduction to symbolic computation. So what does it mean, symbolic computation? Well, if you use a computer to compute something and you use like, let's say, C++ and you use floats or doubles, then you lose precision when you do computation. But when you compute on a sheet of paper, you usually write something like square root of 2 plus something minus something divided by something. So you deal with symbols. And symbolic computation is when you deal with symbols and you are able to compute something. So you have some symbolic expression, and you can compute. Well, you know how to make how to do computation with these symbolic expressions. So you know how to compute. Simply, it means that the result will be a different symbolic computation. So you start with something like square root of 2 plus square root of 3, and you want to multiply it by something, let's say square root of 2 minus square root of 3. So you know that the result will be this. So everything is done symbolically here. And actually, well, the Grosvenor basis is not the only, well, the Grosvenor basis is, will provide you with some things to do this kind of stuff. There are a lot of other techniques, but this is one of them. And well, currently there are a lot of software that can do symbolic computation, and I just want to name some of them. So I believe you know Wolfram Alpha. This is one of the most popular ones. It's free. There are some expensive things like Maple. It's not free. You have to pay like $1,000 million for this. I'm joking, but it's not very cheap. And also, there is a package which is called Sage. It's a package for Python. It allows you to do all of this stuff that Wolfram Alpha and Maple allows you to do, but you can do this in Python. So all these things can do symbolic computations. And if you look inside all of these systems, or inside the package Sage, you'll see that somewhere inside, internally, they use Grosvenor basis as one of the methods to deal with expressions. So let me explain the general idea of symbolic computation. Well, usually, well, you have different symbolic expressions. Well, and you have a way of transforming one expression to another one. And well, replacing one expression by another one, and well, so suppose, well, let me give you an example. For example, you might do something like x square root of 2 and you want to raise it to the second power, then this is exactly the same as 2. So as you can see, this expression and this expression, they're different, but they represent exactly the same value. So you can represent exactly the same value by different expressions. So in order to compare two expressions, so you have expression 1 and you have expression 2, so how do you compare them? Because they may represent exactly the same value, but they may have different form, like here. And you usually have some procedure of reduction of one expression and another one, and if you can reduce them to exactly the same thing, then they're the same. And if you cannot reduce them to exactly the same thing, they're different. So this is some, roughly speaking, the approach that you may use in symbolic computation. And this is very similar to what we will be doing with Grosvenor basis. So if you want to play with Grosvenor basis, you may check this software or this package in Python. So it's really convenient to compute everything using programs, but in the homework, you have to do it by hands because, well, I mean, it's convenient to do it using software, but in order to understand how things work, you should do something by your hands. So I just encourage you to compute everything by hands and just use these packages to check that you're doing everything right. Yeah, but later on, when the algebra course will be over, if you need something for symbolic computation, just I want you to know that there are a lot of software for doing that. Okay, so let me recall what's going on with the Grosvenor basis. What did we do today? I just want a quick recap of everything that was happening during the lecture. So we dealt with the polynomial ring in several variables. And then we need to fix the order of the variables. First of all, we fix, let's say, this order. And then we define a lexicographical order corresponding to the order of the variables. So here I wrote it like this, but this is just a different notation. When I write lex of x1, xn, it means that x1 is the highest variable, x2 is the next one, and so on and so on. So now we know how to compute how to compare all the monomials in this ring. So I cannot use a new variable because I didn't specify how to compare this new variable with the existing ones. So that there was a question at the end of the lecture, why didn't I use variables outside of the set? Because, well, actually the real reason why I didn't do that, because I do not know how to compare new variables with the existing ones. Because the lexicographical ordering is not unique, I have to specify the order of the variables. Okay, now when I have all of these, for each polynomial, well, if I fix a polynomial here, first of all, I can define, well, its leading term, which is CF, the leading coefficient, the leading monomial, and the tail. And this expression is the leading term of the polynomial f. Well, I use the symbol, the index 1 here to specify that this is the first largest coefficient, the first largest monomial, and this is the first largest term. But when I use this notation without the index, I mean that this is just the highest possible here. So this is just the abuse of notation. I hope it should be clear. So now, when I know all these things, yeah, just in case, so this is a coefficient, this is a monomial, and t of f is just the product of a coefficient and a monomial. And this guy is called the tail. What is important, all the summands in the tail, all the monomials inside the tail are strictly smaller than all the monomials here. And if you multiply f by any monomial, then the leading monomial will be the product of the leading monomial with the monomial you multiply by. And all the monomials in the tail will be strictly smaller than the highest monomial. Okay. Now, the second thing we defined an elementary reduction. So if we have a polynomial f and a polynomial g, we can reduce a monomial inside the polynomial f by the leading monomial of g, and we can get f prime. So that's what the procedure of elementary reduction. So there is one remark. This notation actually is not very accurate. It doesn't say which monomial inside f you reduce. So if you want to specify the monomial that was reduced in f, you may write it down here. For example, if your f has this form, something plus cm plus something crmr, and the polynomial g, well, let's say cg mg plus g0, and mg divides m, then so if you want to specify that during this reduction, exactly this summand was reduced by the leading term, so you may write this monomial here under the line. So and now this specifies every information that you need for the elementary reduction. But usually it's not very important which monomial we reduce, especially when later on when well, usually we use this procedure to get to the remainder. And if the order and all the details of the process are not that important, we just skip this monomial here just to save some time. Okay. And yeah, and let me recall how do we do the reduction. So we just need to kill this monomial. And in order to do that, we use the leading part here. We do not reduce it by anything from here. We just reduce it by the leading part. So this guy must divide this thing, and then we just multiply by something in order to get exactly this expression and subtract. And that's why we cancel these summand, and we will get something from the tail multiplied by a coefficient and a monomial. So we replace this thing by a sum of smaller monomials. That was an elementary reduction. We'll get into details when I will do some computation. But just for now, I just want to recall all everything like on this level of accuracy. Now, the next part was to define a reduction of f with respect to a set G. What was that? That was just a sequence of elementary reductions. So we just have a sequence of elementary reductions with respect to some elements of the set G. Then this guy was a reduction of f with respect to G capital. Yeah, and at the end of the lecture, what I proved that the process of reduction will always stop. So if you do several reductions with respect to any set, at the end you must stop. So in this case, this polynomial becomes, well, what are the properties of this polynomial? Well, you cannot make any reduction with respect to G. It means that all monomials inside f prime are not divisible by the leading monomials of elements inside G. And this is your remainder. So remainder is just a polynomial that cannot be reduced by the set G. Yeah, and so let me write explicitly the property of f prime. It means that every monomial in f prime is not divisible by m of g for any g in G capital, whenever g in G capital. So this is the property of a polynomial, which means that the polynomial is a remainder. Okay, so that was a quick recap of what was going on during the lecture. So today I want to go through several properties of the lexicographical ordering, and then I want to compute different reductions, and I want to explain what happens when you change the ordering and how the result changes. Okay, just in case, are there any questions regarding what was going on here? Okay, so now let's discuss properties of the lexicographical ordering. Oh, sorry. So let's take polynomials in two variables. Okay, there are two different there are two different lexicographical orderings. Lexicographical ordering where x is higher than y, and the other one is lexicographical ordering when y is higher than x. Okay, so now what are the monomials of x and y? The monomials are just expressions of this form, where k and m are natural numbers, including 0. So I can represent every monomial as a point on a plane. Let's say here I want to denote k and here m. Then all the monomials are the elements here. Let me write down several of them. So each point here represents a monomial. For example, what is this point? Which monomial does it represent? Well, 1, 2, 3, oh, 0, 1, 2. So it means that we take x to the power of 2, and then 0, 1, 2, 3, which means that we take y to the power of 3. So this violet point represents this monomial. So now, here is the task. I want to describe all the monomials that are strictly smaller than this one with respect to this lexicographical order. So I want to describe all monomials t with respect, which are smaller than this guy with respect to this order. Could you describe, so could you tell me which monomials here are strictly smaller than this guy with respect to this ordering?
Well, kind of the square under it, like, so to speak.
Let me try.
2 points to the left, and
This is the answer.
Yes, this is the square. Yeah.
Okay. Are there any other?
no, probably there are more like 6 points that are on the right.
What again?
Like,
oh, you mean you want to take these guys also?
Well, not those, but in the other side, from m equal 3 and k equal 3
you want to take
k
this one
equal
also?
I guess he wants just to take the borders, not the whole rectangle.
Okay, so
But I'm not sure.
Okay, well, it's not clear to me what you're trying to do, but okay. I mean, am I right that you're saying that we need to add some other monomials here?
Yes.
Okay, which ones? Could you give me an example? Just name the monomial explicitly, x to something, y to something.
Okay, x to the power 4, y to the power 0, for example.
Okay, is this monomial smaller than this one?
Well, probably no. Well,
no, because how do you compare them? First, you compare the power of x, and this one is smaller than this.
It's clear.
So this one is larger.
Then probably the two monomials in the top. So for m, yes.
Okay, yeah, you're right. So these, okay, so let me tell you the answer. Well, actually, the answer is this. This is the correct answer. This set is infinite, so you must take these two columns and all the monomials here. Let me explain why. So let's let's say we take this monomial. What is this?
So the power of the first term should be like equal or less than 2. And if it's less, we don't mind the second one. However, if it's equal, we need the first, like y to the power should be less than 3.
Again, could you just repeat? So if
like
we...
I mean, we have like two cases. The first one, if like the power of x is less than 2, when we don't mind actually the power of y.
Yep.
And
So the case number
equal,
1, yeah, give me a second. So the first case, so when the second monomial is smaller than the first one, the first option is when the power of x is strictly smaller than 2. Then m could be any integer. So this is the case of these two columns. So when k is 0, this is this column, and when the k is 1, it's this column. And here we can take any m. So any point in this column is okay for us. But the other option, yeah, please proceed, is, okay, so let me do this. So the second case is when k is equal to 2, but in this case, we should take m to be strictly smaller than 3. And this represents these 3 points. So here m is 0, m is 1, and m is 2. So as you can see, there are infinitely many monomials strictly smaller than this guy. And this yellow part is just a small part of all the monomials that's strictly smaller than the violet one. So yeah, there are infinitely many monomials strictly smaller than this guy. Okay, but what happens? So let me write this picture again. I believe I should copy paste this picture, but so now the other question is this: what happens if I change the order? If I take x squared y cubed, and I want to describe all monomials with respect to the lexicographical ordering where y is higher than x. And this is k, and this is m. Can you describe what are the monomials here with respect to the other order?
Well, the first 3 rows and right?
This one.
Yeah.
Yeah, exactly. So it works symmetrically. Okay. Now, the other question is, I want to describe all the monomials strictly higher than this one. What can you describe monomials larger than this one? What are the monomials larger than this one on this picture?
Everything else?
Yep, exactly. Everything else, because this ordering is linear. So which color should I use? Let's take the yellow color. So if you take all of these are strictly higher. And the similar thing is here. If you take these guys, these are strictly higher. So yeah, you have infinitely many monomials higher than your one, and you have infinitely many monomials lower than your one. But is it possible to find a monomial such that it only finitely many monomials are smaller than it? So let me write this down. So I want to find a monomial x to the k, y to the m, such that the set of monomials strictly smaller with respect to, say, lexicographical ordering with x higher than y. That this set is finite. So is it possible to find such a monomial? So again, so I want to take a monomial. I want to find all the monomials strictly smaller than this guy with respect to this ordering, and I want this set to be finite. So
probably if the monomial equals 1.
Okay, that's a nice attempt. Yep, exactly. So that's one of the answers. So if you take k to be m to be 0, which means that you have the monomial m, then this set is just empty, because, well, this is the smallest possible monomial, so you have an empty set, and well, yep, in an empty set there are finitely many elements. Okay, and here on the picture, this is this guy. Yeah, so let me write the picture again, but that's not it. I mean,
if k equals
k
0
equals, yeah.
and m equals anything else.
Yeah, exactly. So the right answer is k equal 0. So you take any monomial on this line. So then what are the monomials strictly smaller than this guy? These are all monomials to the left. This is an empty set, and all monomials lower. So this is the set of monomials strictly smaller than this guy. And yeah, so all the monomials are of the form y to the k, where k is just any natural. So they gives you all the monomials with this property. And if you change the order to the different one, where y is higher than x, then the answer will be all the powers of x, because there you have like a different ordering. You just switch the x's. Okay, that's good. Let's move on. Okay. What's the next? Yep, and as you can see, yeah, this the set of these monomials depends on the choice of the order. I just want to clarify this. Okay, the next problem. Give an example of two monomials in oh yeah. So now the next question is this. I just want to take polynomials in free variables. And I know there are like 6 different lexicographical orderings, 6 lex orderings. Oh, because we have 6 options for the order of the variables. And could you give me an example of 2 monomials m and m prime in free variables, such that m is strictly smaller than m prime with respect to every lexicographical ordering here? I mean, could you give me an example of 2 monomials such that one is strictly smaller than the other one for every
X and 1.
Okay, x and 1. Cool. Yep, exactly. Yeah, here you just need only one variable. But can you give me an example of 2 monomials depending on all the variables?
Just powers in one monomial, like all powers should be more than the respective powers in the second monomial.
Yeah, exactly. So what you're saying that you should take m and m prime like this. So m must divide m prime. In this case, so that was one of the properties. In this case, m will be not higher than m prime. And if they're distinct, then m will be strictly smaller than m prime. So
can it be xyz and xyz square?
Yeah, exactly. What's written here.
No,
Yeah.
I mean x to the power 1, y to the power 1, and only that to the power 2.
Oh, yeah, it's also possible to do it like this. Yeah.
Okay, okay, thank you.
Yeah, this is also possible because this guy divides this one, and because of the, well, it doesn't matter which order of variables you take, you have this. So I want to repeat the picture again. So I want to make one additional remark. So if you have a monomial like this, then the monomials divisible by the violet one are these ones. So it's a corner like this. So
I have a question. I don't understand why we can say x, y, and z square and not all of them square. Like,
oh, okay. Give me a second. So okay, so let's
Like it's not less for like all powers except 1, and for 1 it's like more.
so yeah, well, you can fix
Wait,
any
wait.
lexicographical ordering. So you can change the order of the variables. Let's say you may take z, y, x, the opposite ordering, z square y, x, or you may use something like x, z, y, or x, z square y. In all cases, the comparison will be like this, because at some, well, for each variable, the degree of the variable on the left-hand side is either the same as the degree of the variable on the right-hand side, or it's strictly less, as in case of z, than the power on the right-hand side. So if you start comparing lexicographically these two monomials, so if you meet x and y, you just pass to the next variable. And
okay.
if you meet z, okay.
Right. Then another question: why does it have to divide and not just be less or equal to?
I mean, no, I'm okay. No, I'm saying that it's enough to take monomials with this property, then it will be like this. But you can actually prove that. Okay, so okay, let me formulate. Okay, let me erase this and formulate a claim. I'm sorry. So suppose you have two monomials. Such that m is strictly smaller than m prime with respect to, let's say, such that for any lexicographical ordering, m is not strictly, is not higher than m prime with respect to this ordering. So this happens if and only if m divides m prime. So this is the claim. So your monomial m divides m prime if and only if it's smaller than m prime for every lexicographical ordering. So this is the claim.
And what exactly is m?
M and m prime are monomials.
Oh, okay.
In variables x1, xn. So, well, let's explain the right to left direction, then left to right direction. Let's go this. This was just a property. So if m divides m prime, then what does it mean? M prime is equal to t times m. Well, it means that each power of a variable in m prime is either the same as the power of the variable in m, or it's higher. So if you start comparing lexicographically with respect to any ordering, you will get that this monomial is higher than this one, or if t is equal to 1, both monomials are the same. So in this case, this one is true. I mean, I don't know, is this enough, or is it clear, or should I?
Yeah, it's clear, but what
Okay.
about the other way?
Yeah, so the other way is actually simpler. So in order to prove, if you want to prove this, what do you want to do? You want to prove that for any variable, so let's write this like this. and this one like this. So you want, so this happens if and only if di is not greater than di prime. So you want to prove that the degree of each variable on the left is not greater than the degree of each variable on the right, okay? In order to do this, just take the lexicographical ordering like this. Xi is the highest one, and then just arrange all the others in any order. Take this lexicographical order. Then, if you want to compare these two monomials, so you should rewrite them in this form. And how do you decide that, well, and you know, let's say, you know this. So this is what you're given, that for any lexicographical ordering, you have this comparison. Then what does it mean? From this, it follows that di is not greater than di prime, because how do you compare? If di were greater than di prime, then this one would be strictly larger than this one with respect to this ordering. Since we have this comparison, then this one must be either the same as this one, or this one must be strictly smaller than this one. So in any case, this implies this. And this happens for any I. So this simply means that we have all these inequalities. So this means that M divides M prime. Is it clear now?
I mean, okay, yeah, I forgot what it means that one polynomial divides another, so.
Oh, one divides another one when you can multiply these by some other monomial and you will get this one.
Ah, okay, yeah, it makes sense.
Yeah, but when you multiply by a monomial, you can only increase the powers.
Yeah, it's clear, yeah, I see.
Okay, no problem, no problem. Okay, let's move on. What I wanted to do next, I just want to draw a picture once again, and I want to make several remarks regarding this picture. This is the case of two variables again. So if you take a monomial like this, then you have this corner. Well, without your monomial. These are monomials that are divisible by your one. So this guy is, let's denote it by M. Then the yellow angle represent all monomials divisible by M. So M divides T. You can also consider the other part, which is this angle without your monomial M. So this part represents all monomials that divides M. So here T divides M. So this is how the monomials divisible and dividing your monomial look like. So the yellow part is larger than the violet monomial with respect to any lexicographical ordering. And as we have already proven, if you have a monomial which is larger than your monomial with respect to any lexicographical ordering, it belongs to this yellow part. So indeed, if you remember, all the monomials larger than this one with respect to lexicographical ordering where X is higher than Y, what this part, you just cut this, you take this yellow part and all the elements here. And if you choose a different lexicographical ordering where Y was higher than X, you take the yellow part and all these monomials. And when you intersect them, you will get only the yellow part. And the similar thing happens here. Okay, so in some sense, well, lexicographical ordering, it's finer than the order defined by the division relation. Okay, but the problem with the division relation is that you cannot compare this guy with these monomials or these ones, because neither of them divides each other. So in order to compare all of the monomials, you need to find a finer ordering, which is lexicographical ordering. But the lexicographical ordering is not the only possible ordering. There are a lot of other orderings, but I just don't want to make things more complicated, and I just use a very simple family of orderings. Okay, now I want to discuss the division procedure. Let's try to divide a polynomial by another polynomial, and let's see how the procedure works. Oh my God. Yep. Okay, so let's take let's take Q of X, Y, Z, and W, and let's take the lexicographical ordering where X is larger than Y, larger than Z, larger than W. And let's F be Y Z squared W minus X Z W squared. And suppose G1 is X plus Y and G2 is Z plus W. And the set G consists of G1 and G2. And I want to find a remainder of G with respect to G capital. So I want to find a remainder. So I want to be clear. Well, it may happen that we have a lot of different remainders. In this case, well, spoiler, in this case we will have only one possible remainder, but I won't be able to explain it just right now. But let's try to find a remainder. So how do we do this? First of all, let's check if we fixed an ordering. Yes, we have already did that. Then we should find the leading terms in each polynomial G1 and G2. So here is the leading term in G1, and here is the leading term in G2. It's very important when you do this by hands, well, just underline the leading terms. It will help you with not doing mistakes. Now, if we want to find a remainder, we need to find an elementary reduction of f with respect to some of these polynomials, either G1 or G2. In order to do that, we need to find all the monomials here divisible by the leading monomial here. So if you want to reduce f with respect to G1, you need to find inside f a monomial divisible by x, and you have only one option. It's this guy. And if you want to reduce this polynomial with respect to G2, you need to find monomials divisible by z. And here you have two options. You may reduce this part or this part using G2. So let me underline this by the corresponding color. Okay, so let's do it. So how do you do this? So, well, let's try to reduce f with respect to G1. So I want to reduce the monomial xzw squared. Well, so what should you do? Well, you take yz squared w minus xzw squared. This is your f, and you want to subtract G1, which is x plus y, multiplied by something in such a way that you cancel this term. As you can see, you need to multiply by zw squared and also by -1. So if you multiply x by this thing, you will get exactly this term. And when you subtract, you cancel this, and as the result, you will get y z squared w minus plus zw squared y. Okay, so this was one step of elementary reduction of f with respect to g1. Now, just in case, are there any questions regarding this procedure? Okay, so here is a common mistake. There is a very common mistake. You may try to divide, to cancel this term using y, but this will not be an elementary reduction because y is smaller than x. And after this procedure, you replace y by a larger element. So this is something you should keep in mind. So in order to avoid this mistake, just always underline the leading term inside your polynomial g1 and g2, and then you can replace this guy by the tail and not the other way around. I'm saying it may sound funny, but this is a very common mistake, and people confuse the leading term. It may happen just occasionally because you just forget which ordering you're using. In order to avoid this problem, just don't hesitate to underline the leading terms. Okay, so the next remark is this. Let's compare the initial polynomial with the result. You see, we didn't change this term, but what has happened with this one? As you can see, w squared and z are here, and what has happened, we replaced x by minus y. Well, actually, when you reduce, well, if you take a look at the process, when you reduce this element with respect to this polynomial, you actually replace x with minus tail. So if you substitute here minus y instead of x, you will get exactly this expression. So instead of doing this work, what we could do, we could write these directly. So when you reduce this term by this guy, you just replace x by minus y, and the result will be, and it's faster. So you just replace the leading term by the minus tail. So this is how it works, and you can use this to simplify the computation. Okay, now let's proceed. Now I want to be quicker. I hope now it should be clear. So how now you cannot reduce this expression by x plus y because there are no terms divisible by x. Now the only way to reduce this expression is to use the g2, which is z plus w. And now I want to reduce, I can reduce either of the terms. So for example, so this is our leading term. Let's reduce this guy. But how do we reduce? We should replace just one copy of z. Well, let's do it in a fair way. So you take this, and you want to subtract z plus w multiplied by something in order to cancel these elements. So you need to multiply this by y z w. Now, because of this choice, we can cancel, I'm sorry, we can cancel this. And what's left, y z w squared, this is the second term, minus y z w squared. Well, and here, as you can see, we will get 0. So let's take a look. What has happened here? Well, this guy remains the same because we didn't change it. But what happens with this one, y and w remains the same, and then we just replaced one copy of z by minus w. The other copy of z, as you can see here, remains the same. So we're not substituting minus w instead of z here. We just somehow we factor out one copy of z and just replace one copy of z by minus w, and the other part of the expression remains the same. So this is what happens here. And as you can see, the remainder is 0.
So am I correct that we expressed the initial polynomial with g1 and g2?
Yeah, exactly.
Multiplied by some monomials.
Yeah, exactly. As you can see, we have this. First of all, we subtract from f this expression, minus 1 zw square. So we subtract minus 1 zw square g1. This will be the second polynomial. And then we subtract yzw times g2, and we will get 0. So yeah, and now when you rewrite this, you will see that we represented f as the combination of g1 and g2 with monomial coefficients. Well, in general, if you reduce something to zero, you represent your polynomial as the linear combination of the polynomial g1, g2, etc., with some polynomial coefficients. And if you have a remainder, then you will get plus the remainder here. Yeah, but you're right, exactly. So in general, let's say if you do something like this, and probably again g1, it may happen that you can do several reductions and so on, and at the end you will get r. Then if you go through all of these procedures, you will represent f in the form q1 times g1 plus q2 times g2 plus r, where q1 and q2 are some polynomials, where q1 and q2 are polynomials. And r is also a polynomial. So this is somehow the quotients, and this is the remainder. So the picture is very similar to the one we have in the case of one variable. So this is the remainder. In our case, the remainder is 0. Okay, let's do some other computations. Okay, so let's take q of xy, and we will fix the lexicographical ordering where x is higher than y. Okay, and let f be x y square minus x, and g consists of two polynomials, xy plus 1 and y square minus 1. Let's show that f has two different remainders with respect to g. Let's try to find different remainders. First of all, we need to find the leading monomials of our polynomials in the set G. Well, now here it's clear for any lexicographical ordering, this guy will be leading here and this guy will be leading here because y is always smaller. But now so I would like to denote this by G1 and this guy by G2. Okay, let's try to reduce f with respect to these polynomials. Let's try to reduce it with respect to G1. Well, in both cases, only this monomial is divisible by the leading terms of G1 and G2. So what do? We take xy square minus x, and we should subtract xy plus 1 multiplied by y. In this case, yeah, we can cancel the required monomial. And as the result, we will get minus x minus y. And this one is a remainder, because we cannot reduce either of the monomials by the leading monomials here. Okay, let's try the other option. Let's reduce f with respect to g2. So we should take this thing. And the second one is y squared minus 1. So we need to subtract this guy with some coefficient. Which one should we take? We should take x. In this case, we can cancel the required monomial. And what is the result? In the result, we have x minus x plus x. This will be 0. And as you can see, this is also a remainder. So as you can see, during the first procedure, the remainder is not 0. But during the second procedure, the remainder is 0. So, well, when the remainder is 0, it means that you can represent f as the linear combination of g1 and g2. But, if you choose an inappropriate order of the elementary reductions, well, even if you may get a 0 remainder, for the other process, you will get a non-zero one. So that's something to keep in mind. So this is an example of two different remainders. Let's try something else. Let's try the other computation. Let's take f to be x squared y plus xy squared plus y squared, and let's g to be almost the same set, xy minus 1 and y squared minus 1. And the ordering is exactly the same. X is higher than y. Well, in this case, these guys are the leading monomials. And now I want to reduce f with respect to this set. Again, so let this be g1, this one be g2. And I want to reduce f with respect to what? Well, I have a lot of options here. Let's reduce it with respect to g1. But now there are several monomials that I can reduce with respect to g1. I can reduce this monomial, or I can reduce this monomial. Let's write here for clarity which one I would like to reduce. Let's reduce the highest one, which is x squared y. So what will happen here? So in order to do that, I need to subtract g1 with an appropriate coefficient from f. So here, in order to reduce x, so let me underline the leading coefficient and the coefficient I want to reduce. So in order to cancel this one, I just need to multiply by x. Yeah, in this case, I can cancel one by another one. And at the result, and at the end, we will get xy squared plus y squared plus x. Now, I can proceed a reduction with respect to g1, or I can switch to g2. I mean, there are a lot of options, so let's proceed with g1. But now I can reduce this monomial. So when I want to do this, I should subtract xy minus 1 with an appropriate coefficient in order to cancel the leading term. So this is the leading term. This is not the leading term in order to cancel this term. This is the term I want to cancel, and here is the leading term. And here I need to multiply by y. Oops, the wrong color. So here we cancel this. And at the end, we will get y squared plus x plus y. And now I cannot reduce this with respect to g1. Now I need to reduce this with respect to the other polynomial, and the other polynomial is y squared minus 1. And I can reduce only this term. So y squared plus x plus y, I want to reduce it with respect to this guy. And here, as you can see, I just need to multiply by 1 because the leading terms are the same. I can cancel this. and I will get x plus y plus 1. And this is a remainder. So as you can see, well, we cannot reduce this any further. Oh. Okay, what are the other options? Let's try to change. So as you can see, here we have 1, 2, 3 stages of reduction. Let's try to change the reduction from the second step. Let's consider the second step and try to reduce it with respect to G2. And here we have two options. We may reduce the first monomial, or we may reduce the second one. Let's try to reduce the first monomial. What will happen? Well, in this case, we need to do this. This is the leading term, and this is the monomial we want to cancel. In order to cancel this one, we should multiply by x. After doing that, we see that we cancel these guys, and then we will have y squared plus x plus x. So this will be y squared plus 2x. And now, this is still reducible. You cannot reduce this by G1, but you can reduce it by G2 again. And here you can reduce y squared. And again, how do you do that? The same procedure. The coefficient here is 1. So this is the leading term. This is the monomial we want to cancel. So after the cancellation, what will we get? We get 2x plus 1. And as you can see, this is a different remainder. So this is a completely different remainder.
Is there any way to ensure that we get the most optimal remainder?
What does it mean, most optimal?
Means the smallest by like lexicographic order of our polynomials.
Oh, I'm not sure that there is a way of doing that, but there is a better option. We will discuss this during the next lecture. Well, the better option is to change the set G. We actually can extend the set G to a better set such that all remainders will be the same. And now we can avoid this problem of having many remainders. But,
and will they be as good as the best like remainder before we extended the set?
yeah.
Yeah. Great.
And it will give you the best possible remainder. So
I see.
So actually, what will happen? Let me explain why do we need all this technique with division. Well, when we have a polynomial ring in one variable, if you take an ideal, each ideal is generated by one polynomial only. And when you deal with the ring of remainders, well, actually, let's do it without the ring of remainders. And if you have a polynomial here, let's say G, and you want to check if your polynomial is inside I, this is equivalent to saying that G is divisible by F, or F divides G. So now, if you take a closer look to the division procedure, well, this is the polynomial ring in one variable. There is only one lexicographical ordering, which is the ordering by the degree. Then the Euclidean division algorithm is actually, well, how do you check that G is divisible by F? You just divide, so you may reduce G several times by F, well, with respect to the procedure above, and you will get the remainder, which is the remainder in the usual sense. Because how does this process work? You multiply F by X to the power of something with coefficient and subtract from G. Then you multiply F by X to the power of something with coefficient and subtract from G1, and so on and so on. And after this procedure, you will get a polynomial R of degree smaller than F. Well, if it has a monomial of degree equal to F or larger, then you can proceed the reduction process. So after this procedure, you will get exactly what you get via the division procedure. So now, so this is what happens in the case of polynomial in one variable. Now we want to extend this procedure to the case of polynomials in several variables. So we have this polynomial ring in several variables. And if we take an ideal here, it's not true that an arbitrary ideal here is generated by one polynomial, but it can be generated by several polynomials in the following sense. Each element of the ideal is represented in the form like this. Let's say M, where HI are arbitrary polynomials here. So this is how an arbitrary polynomial looks, arbitrary ideal looks like in the polynomial ring in several variables. So it has this form, and this is just a short name for this set. So this is just the definition for this notation. So in order to define an ideal here, you need finitely many polynomials. But now, if you're given a polynomial here, you want to check if it's inside our our ideal I or not. What could you do? You could divide or reduce your polynomial G with respect to the set of polynomials F1, Fm, and you will get a remainder. What does it mean? It means that you represented your polynomial in this form. So if it happens that R is 0, then it's clear that polynomial G is inside the ideal. But if R is not 0, it doesn't mean in general that G is not inside the ideal. It means that you have chosen, well, it may happen that the set F was a terrible set, and that R was just some inappropriate remainder. It may happen that if you reduce it in a different way, you will get a 0 remainder. So if your remainders may be different, well, the fact that R is not 0 doesn't prove anything. But if this set is good, which means it's a Grobner basis, that the remainder doesn't depend on the choice of these elementary reductions, then this remainder becomes a criterion for this problem. I mean, if it's 0, then G belongs to the ideal, and if it's not 0, then G is not inside this ideal. So this is one of the problems we want to solve. So in order to do that, well, it may happen that this initial set is not a Grobner basis, but then we want to change this set to a different one. But we also may we want to change this set to a different one in such a way that the new set, first of all, becomes a Grobner basis, and the second part, it must generate the same ideal. And this is what I'm saying. This is what I mean when I say that you can replace the set by a better set by a Grobner basis for better properties. It means that it becomes a Grobner basis, and it generates exactly the same ideal. And then, for the purpose of this problem, you can replace the initial set by the Grosvenor basis, and you can use the division to find the only possible remainder. Okay, this is somehow an overview of what we're going to achieve. Okay, but let's discuss, by the way, are there any questions regarding this part? But we will discuss it during the following lectures. Okay, so I have like 8 minutes left, so let me discuss several things. Well, first of all, I mentioned that if you take the polynomial ring in one variable, then the usual Euclidean division algorithm is just a partial case of the reduction process we discussed. Indeed, in this case, you have only one variable, and the lexicographical ordering is just the ordering by the degree. So your monomials are just the powers of x. So now if you have a polynomial, something like x cubed plus x plus 1, and you have a this is your f, and you have a polynomial g, which is x squared plus x, how do you divide? By the definition. So you take x cubed plus x plus 1, you write x cubed plus x, and what do? You take the leading monomial here, and you want to cancel the leading monomial here. How do you cancel this? You just multiply by x and subtract. So when you multiply by x, you will get x cubed plus x squared, and when you subtract, you cancel this leading monomial, and you will get minus x squared plus x plus 1. Now you want to divide again. So what do? You want to cancel again the leading monomial here, the leading term. Here it's minus x squared. So in order to cancel it, you multiply by minus 1 and subtract. So multiplying by minus 1, you will get minus x squared minus x. And after subtraction, you will get 2x plus 1. And this guy is not reducible by x squared plus 2. And as you can see, the procedure is exactly the same. So one step here is just an elementary reduction. So this is just an elementary reduction. I'm sorry. It's impossible to write. Elementary reduction. This step is also elementary reduction. So, but when we do it in the way the elementary reduction works, we actually do it like this. We replace f, let's say it's g. We replace it by f minus xg. Then when and we get here some new polynomial f1, which is this guy. This is f1. And then when we want to reduce it again by g, so what we do, we take f1 and we subtract minus 1 times g, and we will get f2. And this is your f2. So this is just a different way of organizing the computation. So the usual Euclidean division is just a partial case of the reduction process we defined here. So you can divide in the same way. But what's interesting here, in the case of Euclidean division, you always divide f by one polynomial. But now it's possible to take two different polynomials here and divide f by these two polynomials. And you may have interesting results. Okay, that was one remark I wanted to make. And the final, by the way, are there any questions regarding this process?
No.
Okay, the second remark I want to make is this. So suppose you have two polynomials, f and g here. And the order, let's say, any lexicographical order is fixed. And suppose that g divides f, so f is divisible by g. Then let's prove that you can reduce f by g to 0. So if f is divisible by g, then you can always reduce this polynomial f to 0. Okay, let's do this. How do you prove this? Well, let's consider an arbitrary sequence of reduction. Well, I will even prove that any sequence of reductions will give you the 0 remainder. So let's consider an arbitrary sequence of reductions. So as we already know, that every sequence terminates. So at some point, we will get the remainder. Okay, so now we want to prove that this guy is 0. Okay, before doing that, let's see. Let's prove the following thing. Let's prove that each polynomial is divisible by g. So we know that g divides f. Let's prove that from that it follows that g divides f1. So what I'm going to prove that if this one is divisible by g, then after the any elementary reduction, the result is also divisible by g. So this is what I want to prove here. But let's skip the proof for now and complete the proof of the whole claim using these auxiliary result. Then you see, because of this result, f is divisible by g, then f1 is divisible by g. Because of the same result, f2 is divisible by g, and so on. At the end, r, which is fk, is also divisible by g. From that, it follows that this guy is divisible by g.
Could you remind, please, what f and g is?
F and g are just arbitrary polynomials, and g divides f. This is all we know.
Okay.
And what I'm saying, if f is divisible by g, then if you take any reduction of f with respect to g, you will always get 0. So I took an arbitrary sequence of reductions of f with respect to g, and I want to prove that the remainder is 0. What I have now, using this property, I will prove it in a second. Using this property, we see that the remainder must also be divisible by g. But if a remainder is divisible by g, and if it's not 0, it must contain a monomial which is divisible by the leading monomial of g. So it's possible to continue the reduction. So if the remainder has this form h times g, then if you multiply g and h, then you will get a monomial divisible by the leading monomial of g. Just multiply the leading monomial of h by the leading monomial of g. So here, when you you have this leading term of h plus the tail of h times leading term of g plus the tail of g. And when you multiply this, you will get this. But here, monomial, so my claim that this guy, you cannot cancel this term. So if you cannot cancel this term, then the monomial of this thing is divisible by the leading monomial of g, because this guy is divisible by the leading monomial of g. And then you can proceed the reduction. So the only thing that we need to show that you cannot cancel this. But why it happens? Well, you see, this thing is contains the highest monomial than every monomial here. And this thing contains the highest monomial than every monomial here. So when you multiply this thing by this thing, you will get a monomial which is strictly smaller than this one. Why? Well, because of the properties. So if this thing is strictly smaller than this one, then when you multiply this by this guy and this by this guy, the comparisons remains the same. So this times this is strictly higher than this times any monomial here. So every monomial here will be strictly smaller than here. By the same argument, every monomial here will be strictly smaller than here. And every monomial here will be strictly smaller than every monomial here, and hence than this monomial. So all the monomials here will be strictly smaller than this one. So if the remainder is divisible by g, then its leading monomial, well, then it contains a monomial which is reducible by g. So R cannot be a remainder, because you cannot reduce remainder. So where is the contradiction? Well, where did the contradiction come from? The contradiction came from the fact that R is non-zero. The only way when R is divisible and we cannot proceed with the reduction is when R is equal to 0. So this is the only option. Just in case, are there any questions regarding this part?
I think yes, because maybe I missed something, but what if it's not, like, if it's not divisible by g, but it's not 0? Why can it be it?
Oh, that's why. There is a part that I want to prove. I still need to prove. If f was divisible by g, then its reduction must be divisible by g. Using this thing, I can apply this for f1 instead of f. And so if f1 is divisible by g, then f2 is divisible by g. And applying this several times, I'll get that fk is divisible by g.
Okay, and where did we get the statement that
This one.
if, yeah.
So this is what I'm going to prove now. But currently,
okay.
what we have is the proof of the claim modular this auxiliary fact. But now I'm going to prove this fact, and then we will be done. Okay?
Okay.
But modular this fact, is it clear what happens here?
Yes.
Okay. Are there any other questions, guys? Okay, so now let me show you why this happens. So if this guy is divisible by g, why its elementary reduction must be divisible by g? Okay, let's prove this. So if f is divisible by g, it's represented like g times h. But now let's take its elementary reduction with respect to g. What does it mean? By definition, the elementary reduction is of the form f minus some coefficient, some term, and the polynomial g. But you see, the polynomial f was in this form, so substituting it here, we see that it's represented in a form like this. So f prime is also divisible by g, just by definition. And that's it. So if this guy is divisible by g and you reduce by g, the result will be also divisible by g. And that's it. Now the proof should be clear, the whole proof. And this is everything that I wanted to tell you today. So are there any questions regarding this seminar? Okay, okay, even Kirill is silent today. Well, then, guys, that was everything. Yeah, but probably the one final remark, we did all the computations in the field of rational numbers, but well, in general, you may use instead of f fields like zp or z5 or etc. Then you just use the logic for the coefficients in the corresponding field. So don't be afraid, it's possible to use any field here. So it doesn't matter which field to use here. Okay, if there is no question, if there are no questions, then that's it. Thanks for being here. I hope that was interesting.
I have a question actually.
Oh, okay. Kirill is now here.
How do we know that t by t is divisible by g in the variant of the like seminar?
Here, do you mean?
No. in the previous task. Yeah, here, yeah.
How do we know that R is divisible by G?
No, T by T is divisible by this red
Oh.
term.
No, it's not divisible by G. It's divisible by the leading term of G. Well,
Okay,
because
why is
this
it
is the
so?
leading term. This is the leading term. What is T? It's a coefficient by the times leading monomial.
Okay.
And how do you find? So in order to make a reduction, you need to find a monomial with coefficient inside F. Or here is inside R, which is divisible by the leading monomial of G. But this is the leading term of G. It's leading monomial times coefficient. And yeah, by the way, if you reduce with respect to a polynomial G1 or G2, just cancel the leading coefficient of G1 and G2. So if, for example, if you, well, in our computations here, let me go up. So if in our computations here, you have something like 2y squared minus 1, just divide by 2 and consider y squared minus 1 over 2. Well, so try to do the reduction in the case when the leading coefficients of these polynomials are 1s. Well, it's just easier to compute if the leading coefficient is 1. So if it were something but not 1, just cancel by this coefficient. Well, you may deal with fractions, but well, in finite fields there are no fractions, so it's easier to do. But well, in any case, it just, your computation become simpler if you cancel by the leading coefficients in every places.
Okay, but why do we need this fact?
Which one?
It's the last one.
This one?
I mean, where R is equal to h by j, h by j, h by j.
Oh, okay. So, okay, let me go through the proof again. So I want to prove that if f is divisible by g, every sequence of reductions gives you 0.
Okay.
I take an arbitrary sequence of reductions and I get some polynomial r. Because of this fact, well, I know if r is divisible by g, then f1, f2, etc., and as a consequence, r itself is divisible by g. So this is what we know. But now what I'm saying, if r is divisible by g, it cannot be, well, and if it's not 0, it cannot be a remainder. I can still continue the reduction process. So if it's not 0, let me show you how to continue the reduction process. And this will be a contradiction because r must be a remainder. So if it's non-zero, in order to prove that you can proceed with the reduction, you need to find a monomial inside R, which is divisible by the leading monomial of G.
Okay,
so this is what I did here.
Okay, thank you.
No problem.
And another question somewhere in the middle. We had two monomials, and one of them was minus x by something.
We had two monomials.
In the very top, it was about
This thing.
no, yeah, where we have yellow and red lines.
Oh, okay. I wanted to show you which monomial is divisible by the leading term. So here the leading term is x, and only this guy is divisible by x. Here the leading term is z, and both monomials are divisible by z. So I can reduce this thing with respect to g1, but I can reduce either of these monomials with respect to g2.
Yeah, okay, this is clear, but what is the leading element in the F?
What is what?
What is the leading element in F?
Oh, okay. The leading, first of all, the leading element doesn't matter in F when you reduce it with respect to some other polynomials.
Yeah, but
if you,
we have some
but if you want to compute, the red one is the leading monomial, because x is the highest variable. So here you have x, and here you have no x. So this will be the leading monomial.
Well, and it doesn't matter whether we have minus in front of the monomial. So
no, it doesn't matter. You may it may have any coefficient.
okay.
So if it has some coefficient, let's say it has +3, then here in order, well, not here. Where was that? No, I didn't do that computation. So if you no, it was somewhere. So if you want to cancel, okay, no. So if you have 3 here, so yeah, and you want to cancel this part, so you have +3. So you just write here instead of -1 +3, the coefficient that you need to cancel the corresponding monomial. So that's a matter of which coefficient you want to put here in order to cancel this sum. Oh, I'm sorry.
Okay, thank you.
Yeah. Are there any other questions? Yeah, I believe well, all the stuff we discussed today is quite simple and everything is straightforward. You just do some computation with respect to some algorithm, and we'll see how many interesting things we can do with this reduction algorithm later on. I hope it will
I
be.
have one more question.
Yep.
Did you notice that during the lecture there was 18 students, I mean 17 students, except for you, and during the seminar there was 15 or 16 of us?
No, actually, I didn't notice the first part. Actually, for me, it doesn't matter how many students came to lecture. So this is my philosophy. I mean, I don't care. Even if just one guy comes, or it doesn't matter. I'll still teach. I mean, for me, it doesn't matter. Well, if you're in, so for me, what is important, if you come here, I assume that this is what you want, that you're interested in being here, that you're interested in the material that we discuss here, and well, it's more convenient for you to be here with me, and it's more convenient for you to listen to me instead of listening to someone else or reading anything else. So I'll just try to do my best, and that's it. For me, it doesn't matter how many of you are here. I mean, it may happen that, well, you're not satisfied by my seminars or by my lectures, and you find a better way of learning all this stuff. That's perfectly fine. I mean, the final goal for us is to teach you. And if my approach is not sufficient for you or is not appropriate for you, and you know a better way of learning, then just go. It's okay. It's perfectly fine. Or there may be any other reason for not being here. For example, well, because of some reasons, you didn't learn the previous lecture and you're not sure that it's a good idea for being here because you don't understand the previous material. Then you may skip this lecture, and instead of the current lecture, you may try to listen to the previous one. So you just don't waste your time. Well, when we discuss a new topic, well, it doesn't matter. But if the lecture depends on the previous one and you don't understand the previous one, the better idea just to skip current lecture and try to listen to the previous one again. So there are many reasons for this thing to happen, and it's okay. It's perfectly fine. So, and that's one of the reasons why I don't like this, you know, negative effects for our tendency. Like, you must attend all my lectures. Come on, it just prevents you from learning. It doesn't make sense to me. I just don't like all this stuff. Okay, I hope it's enough for one monologue.
Excuse me, and where are we going to find the recordings?
Oh, okay. The recordings must be on the YouTube channel. And as I know, well, yeah, there is a problem that I'm not the person who uploading the lectures on the YouTube. There is a special guy in the university doing that. And you know, he needs to upload all the lectures for all the courses. And sometimes if I don't if I don't remind him, he may forget doing that because he has a lot of other stuff to do. And well, in this case, just write me an email or write me via the Telegram, and I will remind this guy to upload the lectures. For example, yesterday, someone wrote to me saying that there is no lecture from the previous week, and I wrote to that guy, and as I know now, there must be the lecture. The previous lecture should be on the YouTube.
And how we can find it?
Oh, you don't
Is
know
there
where
a
to
link
find them?
somewhere? Yeah.
Okay, so let me give you the link. So give me the second. I thought that the problem was that there is no lecture from the previous sem. Okay, so just
Oh, no, just in general. I didn't know that.
okay, it must be here. Give me a second. Oops, I'm sorry. Here is the link in the chat of the Zoom.
Thank you.
Here you can find all the lectures and all our seminars.
Yeah, thank you very much. Goodbye.
No problem. Are there any other questions? Kirill, you're
I
the
guess,
most.
I guess Kirill
No,
has no questions. I hope.
I have some questions about the lecture, but I will read it and ask you later.
Okay.
Okay,
No
Kirill,
problem.
I love to listen to your questions, so that's why I always stay till the end. But then goodbye, I guess.
Okay, then
Thank you
yeah,
for the lecture and the seminar.
no problem, guys. I like that you enjoy the process. It's really important.
Yeah, sometimes it's difficult, but it's interesting.
Okay, then
Yeah.
bye.
Bye.
Okay, thank you. Bye.